Okay, in this video we're going to go over how to work out what type of stationary point you have and whether it be a local maximum, a local minimum, or a horizontal point of inflection. And I'm going to describe how you can work that out and the reasoning behind that. So the first thing I'm going to recognize is this curve here was from a previous video of mine on how to work out stationary points. The way you work out stationary points is by recognizing when does the derivative of your function equal to 0, i.e. when is the rate of change 0? It's neither increasing nor is it decreasing. And on this graph, we have three stationary points. The first type of stationary point that we have is over here. We have what's known as a local maximum. And it's a local maximum because that's not the maximum point of the entire function. That would be over here, and it actually continues even further past that. So we just say it's a local maximum. Then we can also have what's known as a local minimum. And then we can also have what's known as a horizontal point of inflection. Okay, and how we're going to describe this is using the derivative graph. We're going to graph or sketch the derivative of this function. The way I'm going to do that is by using the stationary points. If I know my stationary points are over here, here, and here, I know that on my new graph, and I should actually change this axis here, this axis for this graph here should actually say f-x. This is the derivative. We know the derivative axis will be 0 at the stationary points. Because we know they are stationary points, we know that the y value on our derivative axis will be equal to 0. So what I'm going to do is I'm just going to draw a little dotted line down to this axis here to tell me we have a stationary point here, we have a stationary point here, and finally we have a stationary point here. Now let's identify on our original graph, and I'm just going to get rid of these titles here. We can rewind them to remind yourself what they are. We're going to work out what happens in between the stationary points each time we move across our graph. So whether we move left across our graph versus whether we move right across our graph. So let's first start off from left to right. We'll start over here at this point here. If we look to the left of this stationary point, we can see our graph is only rising. It is increasing and it is getting less positive as we go from left to right. So it is getting less steep. The gradient is decreasing as we go from this point to this point here. But nonetheless, it's still increasing over this function here. So that means the derivative across all points along this function from here to here will always be more than 0. So that means the derivative, our graph, will be more than 0. However, we know it's getting less and less positive. We know it's getting closer and closer to a flat line. So what we can kind of sketch on this function here is some sort of a relationship like this. We know it's positive, positive, positive. We'll even draw it back here, sorry. Positive, 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 until it gets to the stationary point over here. And we know that if we were to match the points along each of these graphs, we can say that it's getting positive but less steep. It's positive but it's getting less steep, and hence it reaches a 0 derivative over here. Then in between these 2 points here, we can say from here to here. So let's say we label this point 1, we label this point 2, and we label this point 3. Between points 1 and point 2, we can see our graph getting more negative. So we'll write it down. It's getting more negative, right? And it is also decreasing. So it is decreasing and getting more negative. And if it's decreasing, then automatically we know that our derivative must be doing something below the x-axis. We know to be somewhere below there. But the way we can draw it is we can say it's decreasing. So we'll draw this point here as well and say technical difficulties. We can say this point here is point 1. We know that at point 1, it is decreasing. It is decreasing and getting more and more negative. until eventually it doesn't decrease anymore, right? It'll still be decreasing, but it's just getting less and less negative, right? It eventually tapers back down over here. So we know it's decreasing and getting more negative, decreasing, getting more negative, until eventually it stops getting more negative. Now we can say from point 1 to this point here, it is now still decreasing, but it is getting less negative. It is getting less negative, so it'll come back up as such. It's decreasing, i.e. it's still below this x-axis, but it's just getting less negative. It's just going back to the stationary point. So it'll look something like this. Obviously, this is not a very clean description of what it should be, so I'm just going to quickly fix this up. It'll look a little something like this. So it'll be like such. So we know it's a minimum over here because we know the rate of change is the lowest. The tangent of the line at this point is the lowest at this point here. So hence, the gradient will be the lowest at this point here as well. Now between this point on the graph to this point, it is almost the identical mirror image of what's going on back here. We can see that it is from here to here, from this point to this point here, we are going positive. We are going increasing. And are we getting more or less positive? Well, we are getting more positive. So if we're getting increasing and we're getting more positive, we know we'll have some sort of a situation like this. And we know it tapers off at some sort of a maximum value because the tangent line, the gradient of the tangent line at this point is the steepest here. So that means the gradient will be reflected in this graph. It'll be a maximum at this point. The gradient becomes a maximum over here. So in sketching this, it'll continue up and up and up until it reaches a maximum over here. Then if we compare from this point here over to this stationary point, we are still increasing. We are still increasing, but now we are getting less positive, less positive. So that would mean we are simply just going back towards being a stationary point as such. Now what can we see? It doesn't just do it like that, it does it something like this. Now what do we do after the stationary point? After the stationary point, we are simply increasing and getting more positive. So that means we are going back up and increasing like that. And this is the sketch of our first derivative graph. Okay, what was the actual significance of this? There were two main reasons why I drew this first derivative graph. The first reason is for the significance, the pure significance of the local minimum points and the local maximum points. And if we compare the local minimum and local maximum points to our original function, so if I just draw a straight line up from that point, it's not that straight, but this point here and this point here, those orange points have a very special name. Those orange points are known as points of inflection. It's known as a point of inflection. And the reason it's called a point of inflection is for one of two reasons. Reason number one, what we can notice is the gradient is the steepest at these 2 points here. It is the most negative, if we draw a tangent line, it is the most negative when we are traversing from this point to this point here. And we can see it is the most positive, it is the most steepest when we're traversing from here to here. So that's why it's first reason why it's a point of inflection. The second reason why it's a point of inflection is because this is where our graphs change concavity. And I'm actually going to draw a new graph just to illustrate the point of concavity. So the 2 points we want to look at is over here and over here. If we were to highlight certain regions of this graph, you will start to recognize something. So let me draw those points which I want you to focus on. The first region is from here to over here, then from here to here, then again from here to here, then again from here to here. What do you notice about the regions in red? What do you notice about the regions in red? But then the regions also in green. Well, what I notice about the regions that are in red is that those regions of the graph there are concave down, i.e. they will have maximum points. So this section of the graph here, it's like a sad face. We're frowning downwards, really, really sad, like a sad face, frowning face. We can see that it also contains the maximum point over there. And what about the green point? The green sections of the graph, sorry. The green sections of the graph is where we're forming happy faces. We're forming concave up regions on our graph. And these regions are concave up, and they will contain your minimum values of the graph. They will contain your minimum values. And so now what do you recognize about where the orange points are nicely located at? Well, the points that are in orange, the point of inflection is exactly where the graph changes concavity. Where the graph changes concavity. So what was the significance on our first derivative graph? Let's now look at this graph here and recognize that the minimum points and the maximum points, i.e. the local minimum and the local maximum on our derivative graph here, was where the point of inflection was located. Now, what I'm going to do to illustrate this even further, is I'm now going to take this exact same graph here. I'm going to take this exact same graph here, and I'm going to do a double derivative graph. I'm going to take a double derivative graph. So from this function here, we're going to draw the new derivative graph here. So how does that look like? Well, it's the same principle as before. I'm just going to copy paste all of this just to save some time. If I wanted to sketch this derivative of my derivative graph, i.e. I wanted to sketch the double derivative function, so f double dash of x. Well, what I can recognize is, first off, this is not the graph. We have to erase all of this. What I can recognize is we can do the same steps that we did in the previous part when we went from our original function to the first derivative. What I can see is these are my stationary points. These are my stationary points. Here, here, and here. So I can see it's flat along these points here. So that means on my new graph, they should be intercepts, because the derivative of my derivative is equal to 0 along these points here. So they should have intercepts here, here, and here. Now we can look left and right along each of these points. So from left of this first stationary point, we can see our graph is decreasing and it is getting less negative. So if it's decreasing and getting less negative, that would mean we are still decreasing. Our function is still below the x-axis, but it's just getting closer and closer to this stationary point here. So it'll look something like this. Obviously, it's going to change in a little bit once I fix it up. But it'll look like this, something along these lines. Then, if we look to the right of the stationary point, we can see it is increasing and getting more positive until this point of inflection here. Remember, the point of inflection is simply the point where the graph is the steepest, i.e. changes concavity. So I know this point here is a point of inflection. So I know from here to here, it'll be increasing and getting positive. So to fix it up a little, it'll look something like this over here. Increasing and getting positive until this point here. And then we can recognize after this point of inflection until the second stationary point, it is simply increasing but then just getting less positive. So it is increasing, so above the x-axis, but just getting closer to the x-axis. And now we can repeat. Because we know this is simply a mirror image of this other region here, we can say it is just going to be a little maximum point like this. Now, if we look at our final stationary point, we can see this stationary point is everything to the right of it is simply increasing and getting more and more positive. So it'll look like this. And that is how you draw your second derivative graph. Again, what was the relevant of this? Now, we need to recognize all three of these together have their own special role. And I'm just going to copy and paste so we can see each of these graphs on one screen. And if we see each of these graphs on one screen, we can very easily recognize what is going on. We can very easily recognize what is the purpose, what is the significance of why we're doing all of this. So have a look here. This was our original graph, f of x, y equals f of x. This was our first derivative graph, y equals f dash x. And this was y equals to our double derivative of x. To our double derivative of x. So looking closely, looking at this equations here, we can recognize three things. The first thing we can recognize is where does our maximum occur? Let's first talk about our maximum point. Well, on the original function, we can see that our maximum point was simply over here. Our local maximum point was over here. If we compare the local maximum point against our first derivative and our second derivative functions, we can see at that point, it was a stationary point. So when we're talking about a local maximum, we can recognize firstly, the first derivative of the function must be equal to 0. That is the first criteria. The second criteria, if we look at the double derivative, is we can see that the double derivative is less than 0 at that point. So our second criteria is the double derivative must be less than 0. And that makes intuitive sense, because if our double derivative is less than 0, we're simply being told that our graph is concave down. And so if our graph is concave down, of course it's going to contain the maximum. Similarly, if we have the local maximum is these sets of rules here, this is very important. If we want to work out the local minimum, how would we work that out? Well, let's have a look in a different color. Our local maximum were these rules here, but our local minimum were these ones over here. Our local minimum sat here. We could see again, it was a stationary point because the single derivative was 0. But then we can recognize that the double derivative of the function at that point was simply more than 0. So that's the two differences between maximums and minimums that we can notice. A maximum versus a minimum, one will simply have the double derivative be less than 0, whereas one will have the double derivative be more than 0. Okay, so we know both of these obviously will have to be stationary points because they're neither increasing nor decreasing. But this is the key distinction we can use when we're trying to work out the differences in minimums and maximums. And last but certainly not least, if we have a look at our third and final stationary point, what we can recognize is this point here is a stationary point again. And all of these, we're comparing different stationary points. So it would make intuitive sense that these points will all have f dash x equal to 0. But what's unique about this one is the double derivative at that point is also equal to 0. And that makes a lot of sense. If our double derivative is equal to 0, we recognize that's where your point of inflection occurs. Your points of inflections, if we have a look over here, that's simply where they intersect your double derivative x-axis. Okay, and we recognize this also intersects the x-axis on our double derivative graph. So what that means is this point here is also what's known as a point of inflection, and we recognize that up here as well in this graph. In this graph, it changes concavity from concave down to concave up. So it changes concavity. If we go back here, it changes concavity. It's a stationary point, but it's a flat point of inflection. It's not like one of these points of inflections where it was like maximum steepness or minimum steepness. It was simply just a flat point of inflection. So hence, for a horizontal point of inflection, we can see that f dash x is equal to 0, and we can also say that the double derivative is equal to 0. And this is how you can distinguish between maximums and minimums, as well as your horizontal points of inflections. Okay, here is our first problem. The first problem is y equals x cubed take 12x squared, and our goal is to first work out all the stationary points, as well as work out the type of stationary point that they are. Another way of saying the type of stationary point is the nature of the stationary point. And for this question here, all I want to work out is just the x values. I don't really care about the coordinate as such. To work out the coordinate, you simply have to work out whatever x value you discover and plug it back into the original function. So first off, where are all your stationary points? First step to work out your stationary points is you single differentiate. You work out the first derivative. Your first derivative for this function is 3x squared take 24x. And you want the derivative to equal to 0 if you're trying to work out your first derivative, if you're trying to work out the stationary point. So 3x squared take 24x equals to 0. That means that 0 is equal to, I can factorize out 3x, and I'm left with x take 8. That would mean, by solving this, either x can equal to 0, or x take 8 equals to 0, in which case x equals to 8. So now we have recognized that we have two stationary points. We have one stationary point here, one stationary point here. How do I know what type of stationary point it is? Is it a minimum? Is it a maximum? Is this one a maximum? Is this one a minimum? Well, screw it. Is this one just a random horizontal point of inflection? How am I supposed to know? Well, we just worked out. In order to work out what type of stationary point it is, we can simply double differentiate. So if we differentiate this function again, and the notation for this is d squared y over dx squared. I know it's a little bit stupid. I didn't invent the rules, but this is how it is. D squared y on dx squared. We just differentiate the derivative function. So if we were to differentiate the derivative function over here, that would be 6x take 24. Now, what is the value of our double derivative? What is the value of our double derivative when x equals to 0? Well, if we plug in x equals to 0, that's the same as 6 times 0 take 24, and that gives us negative 24. And we recognized earlier on that when we had the first derivative equal to 0 and our second derivative be less than 0, in this case it's less than 0, that would be indicative of it being a local max. So our graph is a local maximum at the point x equals 0. And what about when the double derivative, what about when x is equal to 8? Well, 6 times 8 take 24, that's the same as 48 take 24, which is the same as 24. And we recognized earlier when double derivative is more than 0, that simply means that is a local minimum. It is a local minimum. Okay, here's our next question. We're going to find the stationary points of this quartic equation as well as the nature of those stationary points. So first thing we're going to do to work out the stationary points, we're simply going to find the single derivative. And we can use the power rule in this case to find the single derivative. So that would be 12x cubed plus 48x squared plus 48x and plus 0. So that just cancels out. Now to work out the stationary points here, we can simply say we can factorize out a 12x and we're left with an x squared, and then we're left with a 4x, and then we're left with a 4. And in trying to solve this equation, we can say either this has to equal to 0 or this has to equal to 0, and that would be using the null factor law. So when we're trying to say either of these have to be equal to 0, we can say 12x equals to 0, in which case x therefore must equal to 0. Or we can say x squared plus 4x plus 4 equals to 0. And in saying so, we can factorize this as a perfect square. And we can then say x plus 2 must equal to 0 by square rooting both sides of the equation. Therefore, x is simply equal to 2. These are the x values of your two stationary points. But what are these stationary points? Are they local mins, local maxes, horizontal points of inflections? What are they? Well, let's find out. The way we would find out what is our nature of these stationary points is we can simply double differentiate, i.e. differentiate our derivative equation. And in doing so, what we would end up having is d squared y over dx squared. Again, it's pretty useless notation, but it is what it is. So when we differentiate it again, we'll get 36x squared plus 96x plus 48. And I can recognize here that in the process of trying to differentiate this and simplify it, I can factorize out a 12. And I'll be left with a 3x squared plus 8x plus 4. And I can factorize this one more time by saying 12 times, and think of two numbers that would both add to 12, add to 8, but times to 3 times 4, so times to 12. And in recognizing this, I can see that 6 and 2 work just fine. So in trying to factorize this, I can say we'll have a 3x take something, 3x plus something, and then x plus something. And I can see that we would have 3x plus 2, 3x plus 2. That's what I think will work. And the reason I'm saying this is 3x squared is 3x squared. 3x times 2 is 6x. This times this is 2x, so that's 8x, and then 2 times 2 is 4. So that works out. Now that we have this, we need to work out what is the values of the double derivative. What are these values when x equals to our stationary point? So when x equals to 0 and x equals to 2, what are the values? So when x equals to 0, we'll work that out first. So we know that this is just subbing in 0, so it'd be 3 times 0, 0 plus 2. That would simplify down to 12 times by 2 times 2, which is a positive number nonetheless, but what it equals to is 48. So therefore, because d squared y over dx squared, but i.e. because your double derivative is more than 0, we can say that at x equals 0, it is a local, is it a local minimum or a maximum? Well, if you said local minimum, you would be absolutely correct, because our graph is concave up, and if it's concave up, it will be a minimum. Now we just have to do the same thing for the other value of our double derivative, which is x equals 2. So when we're solving for this, we know that d squared y over dx squared is simply equal, when x equals to 2, is simply 12 times 6 plus 2 times by 2 plus 2. And I got 6 by simply doing 3 times 2. And that would be equal to 12 times 8 times by... Have I solved this incorrectly? Okay, I have solved it incorrectly. I meant to say x equals negative 2. Okay, so now let's actually solve it properly. In doing so, we can say this is equal to minus 6, not 6. And we can say this is equal to minus 2. And because we have just got this part equaling to 0, so we can say this is times by 4, and this is times by 0, this gives us a 0. And what we can say here, I'll tell you when there are cases when you can't say this is simply a horizontal point of inflection. Right? Because your first derivative is equal to 0, and your double derivative is equal to 0, we can say that this gives us a horizontal point of inflection. All right, this is our next question. Our next question is x squared ln x. And pause the video to give this a go yourself. All right, good. So if we wanted to work out the stationary points for this question here, we're going to work out what is f dash x, what is our first derivative. Well, in this case, I recognize that I have one function multiplied by another function. And in that case, I would simply use the product rule. So in trying to differentiate this, You differentiate the x squared to get 2x, and then you leave the ln x as is, and then you do the opposite. You keep the x squared, but then you differentiate the ln x. Now when you have this, you can simply factorize it and simplify it in the end as well. You will have 2x ln x plus x, and then you can factorize out the x to get 2 ln x plus 1. And you know, if you want to work out the stationary points, you want the first derivative to equal to 0. So now we're simply going to solve this equation for 0. And we can recognize that we have one function here times by another function here equaling to 0. So that means we can use the null factor law. So either x has to be equal to 0 or 2 ln x plus 1 has to equal to 0. And when we solve for this, we can say ln x is equal to negative a half. And then we can say, to get rid of the ln, we can raise both sides of the equation to the power of e. This and this cancel. This and this cancel. So then we can say that x is simply equal to 1 over the square root of e. 1 over the square root of e. Okay, so those are our two stationary points. But what are those stationary points? Are they minimums, maximums, or horizontal points of inflections? Well, let's work it out. To work out whether this is what type of stationary point this is, we simply need to work out what is the double prime, the double derivative of the original function, i.e. the derivative of our derivative. So in this case, we would try to differentiate this equation here, because this is the simplified equation up here. So in doing so, I can recognize we have product rule here in this term here, and then this is just a single term we can differentiate on its own. So now what I'm going to do is I'm going to differentiate this green term here using the product rule. So we can say the derivative of that is keep the 2x, differentiate the ln x, so 1 over x, plus do the opposite. Differentiate the 2x, so that's 2, and then keep the ln x. And then the derivative of this bit here is just plus 1. So now when you're trying to simplify this, this simply becomes 2 plus 2 ln x plus 1, which is also the same as just 2 ln x plus 3. And now let's work out the value of f double prime when x is equal to 0. So 2 ln of 0 plus 3. Well, we know that this value here is pretty much undefined, and I'll tell you what to do that in a sec, what to do. But we also have the value e to the power of negative a half, or 1 over square root e. So if we're trying to work out the double prime of this is the same as 2 ln of e to the power of negative a half plus 3. And we know that ln and e simply cancel out, so we're left with 2 times negative a half plus 3. And that'll give us a value of negative 1 plus 3, which is equal to 2. And because the double prime, or the double derivative of e to the power of negative half is more than 0, we can say that when x equals to e to the power of negative a half, when it's x equals to e to the negative half, it gives us a local minimum, because this value is more than 0. Alright, and the last example we're going to do is x takes sine x. And first thing we're going to do is work out the stationary points of this function by simply differentiating. The derivative of x is 1. The derivative of sine x is simply cosine x. Now that we have this, we can let our function equal to 0, because we're trying to find when our stationary points arise. And we can solve the equation for cos x equals to 1. And I'm going to just write a little boundary here. I'm going to say our solutions are going to be between 0 and 2 pi. So continuing on with this, I can say that cosine equals to 1 when x is equal to either 0 or when x is equal to 2 pi. Those are my two solutions that I could have. I do have another video that's on how you can find the solutions to trig equations, so be sure to watch that when it's up eventually. Now, we can work out these are our stationary points, but what are the nature of these stationary points? Well, double differentiate. The derivative of our derivative is simply equal to minus sine x. Now let's work out the double derivative when x is equal to both 0 and 2 pi. When x is equal to 0, we know that it's minus sine of 0. And we know that sine of 0 is simply just 0, right? So what we have to do when we get a 0 is we have to do some more investigation, which I'll do in another video. But this, we need some more investigation. Needs more investigation. For now, though, I will say it is a horizontal point of inflection. And then when our double derivative equals, what is our double derivative when x is equal to 2 pi? Well, it's just minus sine 2 pi. Right, and minus sine 2 pi is simply also equal to 0. And we need to also do some more investigation on this as well.